Imagine you need to gzip a 2 GB log file and upload it to a remote server. You write the obvious Node.js code, read the file, compress it, send it. You run it. Your server crashes. Not because of a bug, because you just tried to hold 2 GB in RAM all at once. This is the buffering problem, and it's one of the most common ways Node.js applications fall over under real-world load. The buffered API works in a simple, sequential way. You call readFile, Node.js waits until the entire file is loaded into memory, then hands it to your callback. From there you compress it, still in memory, and only then do you start sending it. At peak, you might be holding the original file, the compressed copy, and some encoding overhead all at the same time. With a 2 GB file, that's a lot. With 100 concurrent users doing the same thing? That's potentially hundreds of gigabytes. Streams solve this problem at the architectural level. Instead of reading the whole file and then processing it, a stream processes data in small chunks, typically a few kilobytes at a time. The chunk arrives, gets compressed, gets sent to the network, and leaves memory. By the time the second chunk arrives, the first is gone. The difference is not a minor optimization. It's the difference between a system that works and one that crashes under load. Node.js was designed around this model from the very beginning. The HTTP module, the file system module, the crypto module, the compression module, they all speak the language of streams. Understanding streams is not optional knowledge in Node.js. It's foundational. And once you see how streams compose together, you'll wonder how you ever thought about data processing any other way. Let's make the memory argument concrete with a real scenario from the book. You have a large file, think a multi-gigabyte video or database dump. Your task is to gzip it. With the buffered approach, the entire file must live in memory before a single compressed byte can be produced. If the file is larger than your available heap, which in Node.js defaults to roughly 1.5 gigabytes, you hit a fatal error before you even start compressing. Try it yourself. Write a Node.js script that calls fs.readFile on a 2 GB file and you'll see JavaScript heap out of memory. The process dies. Not gracefully dead. Now contrast that with the streaming approach. You create a readable stream from the file. You pipe it through as lib.createGzip, transform stream. You pipe the output to a writable file stream. At any given moment, you're holding maybe 64 kilobytes in memory, the size of a single chunk. It doesn't matter if the file is 2 gigabytes or 20. Your memory usage stays flat. Here's the math that makes this dramatic. A 2 GB file processed with buffers might require 6 GB of RAM when you account for the original data, the compressed output, and working space. The same file processed with streams requires roughly 64 kilobytes, that's a factor of 90,000 times less memory. This is what the book calls spatial efficiency, using space in proportion to what you actually need to work on, not in proportion to the total size of the data. And here's the key insight: streams don't just save memory, they enable processing of data that would otherwise be impossible. A file larger than your RAM is not processable with buffers. With streams, size becomes irrelevant. Spatial efficiency is the first reason streams exist. But it's not the only one. Here's a question worth sitting with: in a buffered pipeline, when can you start uploading compressed data to a server? The answer is, only after compression is completely finished. You read the whole file, compress the whole file, then start the upload. These three phases happen strictly one after another. Total time equals read time plus compress time plus upload time. With streams, something much more interesting happens. The moment the first compressed chunk is ready, after processing just a few kilobytes, it can go onto the network. Compression doesn't need to wait for the whole file to be read. Upload doesn't need to wait for compression to finish. All three operations overlap. This is called pipeline parallelism, and it's the exact same principle that makes assembly lines efficient. A car factory doesn't wait for one car to be fully assembled before starting the next. Each station works on a different car simultaneously, and the total throughput is far higher. The time savings can be significant. Imagine reading takes 10 seconds, compressing takes 8 seconds, and uploading takes 15 seconds. Buffered, 33 seconds total. Pipelined, roughly 15 to 17 seconds, because all three phases overlap for most of the duration. You've cut total wall clock time nearly in half, not by making any individual operation faster, but by letting them run concurrently. The book calls this time efficiency. And unlike spatial efficiency, which is about avoiding crashes, time efficiency is about being genuinely faster, even when memory isn't a constraint. These two benefits together already make a compelling case for streams. But there's a third one that changes how you think about software architecture. The most elegant thing about streams in Node.js is not their memory efficiency or their performance. It's how they compose. Streams expose a consistent interface. A readable has a readable end, a writable has a writable end. The pipe method connects them. This is exactly how Unix pipes work at the shell level. You chain commands with the pipe operator, and data flows through each one in sequence. Node.js streams bring that same philosophy into JavaScript. Consider this pipeline: you read a file, pipe it through gzip compression, pipe it through AES encryption, and pipe it to a network write stream. In Node.js, that's literally 4 lines with pipe calls. Each piece does exactly one thing. Each piece is independently reusable. Now imagine you need to add client-side encryption to an existing pipeline that currently just compresses and uploads. With buffered code, you might need to restructure the whole thing. With streams, you insert one more pipe call between compression and upload. The rest of the code is untouched. The reading code doesn't know about encryption. The upload code doesn't know about compression. Each stage is isolated. The book points out that composability is what makes Node.js streams so powerful for building real applications. You can mix and match built-in streams with custom ones. The zlib module gives you a gzip transform. The crypto module gives you a cipher transform. You can write your own transforms for custom processing. And they all connect with the same pipe interface. This is the third reason streams matter: they make complex data pipelines simple to build, easy to extend, and clean to test. Spatial efficiency, time efficiency, composability, together, these 3 properties explain why streams are at the heart of Node.js design.